Hi. So in today's lecture, we will be discussing this topic, which is big data, a primer. So what I hope to achieve in this lecture is to be able to define what big data means. I am personally very guilty of using the word big data very casually. I used to think that big data is just a way of describing that, oh, the data is increasing, the data is increasing. But what I've realized is that when you use the word big data and when you say that you want to adopt a big data solution, it means something different. It is not a very vague term anymore. It is relatively well defined. And I therefore hope to spend considerable amount of time explaining what big data is as I understand it. After successfully defining what big data is, I will talk about the big data solution in terms of hardware and software. That will naturally lead us to describing Hadoop. We will not become experts at Hadoop in this limited amount of time, and neither am I the right person to explain Hadoop in great depth, so this will be a very shallow dive, and we'll briefly explain what lies in terms of technology beyond Hadoop. Then we will come to databases. We will understand, again, a shallow dive. We will try and understand some basics of relational database systems, then head towards NoSQL and eventually talk about the CAP theorem. Towards the end of my talk, what I also hope to do is give you some basics of cloud computing with an emphasis on its relevance to big data, and then we can have a discussion where maybe I will be able to give you some recommendations or strategy to adopt for possible questions or problems or scenarios that you may want to suggest. All right, so let's begin with the definition of big data. Now, this is something that has escaped me for quite some time. I really did not know how to define big data. I saw various definitions, some convincing, some not convincing. But eventually, the most appealing definition that I came across was the following. And before I go any further, a disclaimer here. This lecture or talk is highly opinionated. By that, what I am trying to warn you is the following. You should not use the material that is present in this lecture to go and argue with someone or explain to someone what big data is. If there was an information technology professional who has worked in big data for several years, they would probably not want to explain big data the way I am going to try and explain to you. I am giving a very, very shallow overview of this topic, but somebody could go in much greater depth. So definitely don't treat this as textbook material or as gospel and have conversations with people on it. This is just for you to get acquainted with the field, and then you will have to find more concrete and formal sources to cement your understanding of the various topics that I am about to present. So let's come back. What is big data? As I said, there are many ways of defining. This is the definition that appeals to me the most. It is a phrase used to characterize data that is not easy to handle using traditional solutions. By far, this is the best definition I have found, for myself at least. But there's a problem with this definition. For this definition to be complete or to make sense, you first have to define what is a traditional solution. And then you have to ask the question, when does it become not easy to use a traditional solution? And that is what the next few minutes are all about. So let's talk about traditional solution from the point of view of hardware. So it generally is a single unit hardware. It could be your laptop, it could be your desktop, or it could be a server class machine. It comprises of a single CPU. Generally, in the case of a laptop or a desktop, you have only one CPU which has many cores on it. Or in the case of a server, you could have multiple CPUs, each having multiple cores. Then we have the main memory in the form of RAM chips. Generally, most laptops equip themselves with one chip, max two chips. Same is the case with desktops. But servers can actually go up to 8, 12, 16, any number of chips, depending on how big the hardware is and how expensive the hardware is. As far as data storage is concerned, in case of laptops or desktops, we usually talk about a single disk. Whereas in most of the servers, we usually have what is called as a RAID storage. So RAID stands for redundant array of inexpensive disks, and we will spend a minute talking about RAID since the topic has been introduced. Okay, so each slot that you see here is a inexpensive disk, which means it is a perfectly normal hard disk. It could be a 5400 RPM or a 7200 RPM magnetic disk, or it could be a solid state disk, but it is an ordinary disk. There's nothing super special about it. Now we have an entire array of these inexpensive disks, and there is a special unit of hardware called as a RAID controller. And the RAID controller achieves three things. The first thing is that it gives us a unified view of the disks. So if you had an array of 10 disks and each disk was 1 terabyte, then its job is to give you the illusion that there is only one hard disk which is 10 terabytes in size, loosely speaking. The second important function that this RAID controller achieves is something called striping. So imagine that you are trying to copy 900 GB of data. What the RAID controller could do is it would split it on the spot into three pieces of 300 GB. One of the hard disks will be made in charge of one unit of 300 GB. Another hard disk will be made in charge of another unit of 300 GB, and so on. So when you write this 900 GB, you have three independent disks doing the write. Therefore, you achieve very high speed of writing. And that is what we call striping. The next major function that RAID controllers perform is replication. So let's imagine that one of your disks fails, right? You have so many disks that it is easy to imagine one of the disks failing. But the problem is that your data is stored across everything. So even if one of the disks fails, the integrity of your entire data could go for a toss, which is why when you have such a large collection of disks, it is important to have redundancy, that is, maintain duplicate copies of the data across the disk, so that even if one disk fails, it is possible for us to recover data from another disk, and that buys you some time to quickly replace that disk. And when you replace the disk, the RAID controller also restores the original data by copying it from other sources. So this is what RAID is. So going back to this slide, we spoke about RAID from the point of view of storage. So whenever you have a server machine, and the storage is typically in the form of a RAID array. Now let's talk about the software part. The operating system is your standard operating system. So if you're running Ubuntu on a laptop, then you would also run Ubuntu on a server. If you're running Windows on a laptop, then you would run Windows on a server as well, albeit with slight modifications. Otherwise, everything more or less remains the same. When you want to write programs, you would use the same old programming. You would use the same Python program, but it would run faster on a server. It would run slightly slower on a laptop. But on a server, you generally have many cores and CPUs, in which case if you want to benefit from multiple cores, you may use techniques or libraries such as MPI or CUDA in order to achieve multi-core processing. If you wanted to store your unstructured data, you would store them in the form of files, either on your disk or on your RAID storage. And if you had a structured data, you would use typically a relational database. The examples include MySQL, Postgres, Oracle, etc. Now, an important question when understanding big data is, suppose I have a traditional hardware software solution and one day I discover that the system is running too slow because the CPU power is not enough, or I find that the RAM is no longer sufficient enough, or I find that we are out of hard disk space. What are the options that we can have? One possibility is to look for expansion, but expansion is not guaranteed. In fact, if you have a weak CPU, then there is no way to suddenly speed up the CPU. You will have to buy a new one. If you are out of RAM, maybe you can add a few RAM slots, but that also is not guaranteed. If you are out of storage, maybe you can buy a couple of more disks. So most of the times you end up buying a new one. But whenever you buy a new one very important thing that you have to do is migrate. Migrate means you have a machine which is sitting there and you decide to upgrade. So you buy a completely new machine. Now you have to install your operating system and software and everything on that new machine. Then you have to migrate your data from the old machine to the new machine. So there's a very big headache involved whenever you run out of computational or storage power and you have to migrate to a new hardware. This method of scaling your computational power or your storage requirements is called vertical scaling. So vertical scaling is another way of saying that you have to buy a new piece of hardware and you can't augment to the existing capacity easily. Now, when you have a traditional hardware, the next question is, when does this traditional solution become weak? So what is it that causes a strain on the traditional solution? Because remember, we are trying to define big data, and I said that big data refers to data that makes traditional solutions infeasible. So we have understood what a traditional solution is. We are now trying to understand what makes them infeasible or strained. So here I'm going to invoke the famous 3 V's of big data, starting with volume. So what do you think the volume of the data should be to strain our computer? It should obviously be high. But what is very important to understand here is that it's not just enough that your total volume of the data is very high. Now, if I may share an anecdote or an event from my career here, I used to be in charge of a server where we had stored data from a survey called as the CRTS, the Catalina Real-Time Transient Survey. This was about 8 terabytes of images and 8 terabytes of photometric data. And whenever I used to talk to my colleagues outside of astronomy, and I used to tell them that these are the volumes of data that I deal with, they would say, yes, it's big data indeed. But when they saw how this data was being handled, they found that there was absolutely nothing new about the method of handling the data that we were doing. But then, and the reason is simple, because even though there is 8 terabytes of imaging data present on that computer, at any given time I'm working with only a few megabytes. I will take one image and process it. Each image is like a couple of hundred of kilobytes or maybe a few megabytes. But take a counter example, and this is from again, I was talking to this friend who was working on DNA sequence data processing. There, a single DNA sequence was about 500 gigs in size. However, you could not work with 1 gigabyte at a time. You had to process the entire 500 GB in one go to extract the DNA sequence. And that is something that a normal computer could not do. So The lesson here is that yes, the volume of the data should be high to qualify as big data, but it is not just the total volume, but the volume that needs to be processed in a single go. So even though 500 GB of DNA sequence data is lesser in volume than 8 terabytes of CRTS imaging data, a single unit of CRTS imaging data is only few megabytes in size, whereas the 500 gigs have to be done or treated as a single machine, a single unit. The next V is velocity. The velocity is the rate of acquisition of data or generation of data. Obviously, to qualify for big data, velocity has to be high. But again, it is not enough that you are just collecting data at a high rate. So here's a simple example. You have a telescope. That telescope has some state-of-the-art instruments on it, and it is generating immense amount of data, right? Maybe a couple of gigabytes per hour or tens of gigabytes per night, whatever. But here is the deal. The telescope takes the data. Somebody has requested that data. Nothing generally happens which is drastic when the person gets the processed data delayed by a week. So if you're not in a mood, you spend a couple of days relaxing, and then one day you wake up and you say, okay, I have nothing better to do. Let me take the data that I had observed a couple of nights before and let me process that data. And then you process the data. It takes a couple of hours to finish off, or maybe even a couple of days. Then the data is ready. Then you put it up on a server. Then you tell the person who requested the data, take it. And nothing happens. But let me give you a counter example. And this is the example of algorithmic trading. So what happens here is that we have the world's stock exchanges. There's trading going on, and those trades or transactions that are carried out generate an immense amount of data. And that data could be a couple of gigabytes per hour, per minute. I do not know. I don't work in algorithmic trading. But here is the important point. You cannot sit on that data and wait casually. Because in algorithmic trading, you want to use the data generated immediately to decide what is the next transaction that you must perform a couple of seconds or a second later. Which means that your data is being collected at a fast rate, but it also needs to be processed at a fast rate in order to be meaningful. So that is what I mean when I say that it's not just enough that you're collecting data at a high rate, you have to deliver data at a high rate. So if I had to choose an example of the high rate of processing in astronomy, imagine a telescope whose job is to look for near-Earth objects coming close to the Earth. It is repeatedly scanning the sky and generating images, and you have a software which is going to look at those images and try and detect near-Earth objects. Then if you want to sensibly detect these near-Earth objects and warn people that there is an object dangerously close to the Earth or passing through, then it better do processing at a fast rate. Unlike observations of galaxies, for example, where you can actually wait for a couple of days easy before you process the data. The third V of big data is variety. Variety is the very different kinds of data that you're dealing with. And again, it's just not enough that your total variety is high. Because, for example, you have images, you have spectroscopy, you have photometry, you have all kinds of data. There are different varieties, therefore big data. No, that's not the point. How much of this data do you need to handle simultaneously? Do you often need to handle photometry and images together? Very rarely, or maybe not at all. But on the other hand, consider, say, a loan application. A loan application has well-defined structure, but it also is accompanied with a lot of unstructured data, like scans of salary slips and maybe income tax returns and maybe some other accreditations and so on. And you need to process all of this data and store all of this data together, and therefore there's a huge variety, and it simultaneously it needs to be accessed simultaneously. So that would qualify as a high variety problem, but not when just that the total variety is high. So in summary, We can define big data as a phrase used to characterize data that is not easy to handle using traditional solutions. And we have covered using the 3 V's when it is not easy to handle the data. And we have also defined what a traditional solution is. Just as a reminder, a single monolithic machine with conventional software is a traditional solution. And this is how I prefer defining big data. So now that we have defined big data, we need to understand what big data architecture looks like. How is it different from a traditional solution? And that comes in the next part. This is a good time to pause for a while.